For another major example of Euclidean domains, we have polynomials over a field K. We've used these examples before, but we've often invoked properties without giving proofs. So here we provide the details. Now, recall, K adjoint X is just going to be the set of polynomials in the variable X with coefficients in the field K. So we have items like a sub n x to the n, a bunch of pluses going all the way down to a sub 1x plus a sub 0. The a's are all going to be in our field K. Now, we have the usual addition, subtraction, multiplication, and long division of polynomials here. So we'll get a Euclidean domain from long division. And in this case, the d function is just given as the degree of a polynomial. For instance, if we want to find the units, we find all elements with d equal to d of 1. And in this case, the degree of the constant function 1 is 0. So we're just going to get the non-zero constants, or all elements of k, throw away 0. Now, for the division algorithm, okay, this is just the usual long division of polynomials. We have f and g, okay, g non-zero. We can always solve for q and r in the equation, f equal to g times q plus r, where the degree of r is strictly less than the degree of g, or r is equal to 0. So let's show this. We give our proof by induction on the degree of f. So if the degree of f is 0, then f is some non-zero constant k. Then we have two cases. If the degree of g is also 0, then it's some non-zero constant k prime. And I can write f as k times k prime inverse times g. And then that's our equation. Otherwise, okay, if g has positive degree, then I just let q be equal to 0 and r equal to k. Again, that gives our equation, and then that's our base case. Now, for the induction step, we just assume it's true when the degree is equal to n minus 1 for f. We'll show that's true when the degree is equal to n. So I'll assume that f is equal to a sub n, x to the n, and so on. We'll assume that g has b to the m, x to the m, and so on, and n is greater than or equal to m. Now, that means I can write f as g of x times a sub n over bm times x to the n minus m plus another polynomial with degree strictly less than n. For this polynomial f1, we can invoke the induction hypothesis. So I can write f1 as g times q plus r, where degree of r is strictly less than degree of g, or r is equal to 0. Now we just substitute. So I have f of x written as, okay, we have g of x times some polynomial q prime, plus the r of x that we were looking for, with the correct condition on degree or being equal to 0. So that's our induction proof. We also have condition 2 in the definition of Euclidean domain. F and g are non-zero, and d of f is less than or equal to d of f times g. This is straightforward for the degree function. And we note we use this property to guarantee finite factorization of non-zero elements into primes. Now, Euclidean domain implies PID implies UFD. Whether the irreducibles and primes are the same in K adjoint X. We have another notion of irreducible for polynomials, which isn't quite the same. So, a non-constant polynomial f of x in K adjoint X is called irreducible over K if and only if, whenever f of x is equal to g of x h of x, with g and h in K adjoint X, then we must have that one of g or h is a constant. So in this definition, it's with reference to a given field K. For instance, if we're working over the reals, then x squared plus 1 is irreducible. But if we move over to the complex numbers, it becomes x plus I times x minus I, and that's not irreducible in C adjoint X. Now, if we weaken the condition of working over a field, okay, what can happen? So for instance, if we switch instead to the integers, okay, z adjoint x, we've seen that the ideal generated by 2 and x is not a principal ideal. So this is not a principal ideal domain, which means it can't be a Euclidean domain. On the other hand, it's still a unique factorization domain, and we'll see that later. Now, back to k adjoint x, we have a UFD, so we're able to get finite factorizations into primes. Those factorizations are unique up to units. So we want some factoring rules. So these should look familiar from basic algebra. First, if I have an alpha and k, a root of our polynomial f of x, then x minus alpha divides f of x. This is just an application of the division algorithm. So here, I'll let g of x be equal to x minus alpha. I can write f of x as x minus alpha q of x plus r of x. The condition on r just reduces to r being a constant function. If we evaluate at alpha, what happens? Well, f of alpha is 0 by assumption. I have alpha minus alpha, so this goes to 0. And that leaves r of alpha equal to 0. Because r is a constant, that constant's equal to 0. And that means we have division as promised. So f of x is just a multiple of x minus alpha. Next, k is a field. F is not exactly equal to 0. If f has n roots, then n is less than or equal to the degree of f. To see this, we choose alpha and beta not equal roots of f. By the proposition, f of x is equal to x minus alpha g of x. We evaluated beta, so f of beta is equal to 0, but now it's also equal to beta minus alpha times g of beta. Because beta and alpha are not the same, this is non-zero, because we're in an integral domain that forces g of beta to be equal to 0. We invoke the proposition again, so I can write g of x equal to x minus beta h of x. We substitute, and then I have f of x equal to x minus alpha, x minus beta, h of x. And we keep continuing this process for as many roots that we have. So, statement, we use induction to prove it. If alpha 1 through alpha n are distinct roots of f of x, then I have x minus alpha 1 product through x minus alpha n divides f of x. Because this polynomial on the left-hand side has degree exactly equal to n is less than or equal to degree of f, which is what we're looking for. Now, when do we have strict inequality? When we have repeated roots, or when we have an irreducible polynomial, okay, when we factor with degree greater than 1. Now, in general, there's always going to exist a larger field such that f will have the correct number of roots, counting multiplicity, in that field adjoint x. So what this just means is that our polynomial will factor completely into linear factors. So the way we get this, if we have f of x, okay, in k adjoint x, irreducible with degree greater than 1, I'll just form the quotient ring given by taking k adjoint x, mod out the ideal generated by f of x. Now, because f of x is an irreducible, okay, the same as a prime, that means this is equivalent to being a maximal ideal, and the quotient's going to be a field. We note this f is no longer irreducible over this ring, because we note f is now going to have the root x plus the ideal generated by f of x. So this coset, when we put it through the polynomial f, is going to give us 0 as the 0 coset. For a concrete example, let's consider f of x equal to x squared plus 1 over the reals. Now, x squared plus 1 is irreducible, so if we take the ideal generated by that, we'll have a maximal ideal. Then we take the quotient, we get a field. Note here, okay, f is a polynomial, but we think of it in purely symbolic terms. It says, take whatever we put in here, square it, and then add it to whatever 1 is. So inside of this field, if we put in x, okay, that's the coset for x plus I, we're to square it and add the ideal associated to 1. Now we can expand all of this, and then we note, okay, this is an I, this is an I, this is an I, this is an I, and what we get is x squared plus 1 plus I. But because x squared plus 1 is already in our ideal I, this is the 0 ideal. So we have the f on this coset is 0. So this coset is going to be the root we were looking for f. Now, when we factor, okay, I can't use x for the variable. I'll just use this capital X. I'll have f of capital X equals x minus coset for little x times x minus coset for minus little x. And that's our factorization for this polynomial now. All right, we normally don't think of this scenario in this way. Okay, instead we just think of take r join x, mod out by the ideal x squared plus 1. That's going to go to the complex numbers just by evaluation at I. So we just send coset for a plus bx to a plus bi. Now, in general, okay, when we do this process, it might not stop at k1. We may split off a root, but there may be irreducible factors left over in f. So we'll have a k2, a k3 until our process stops and f is completely factored. Now, let's see this process in concrete examples. Okay, in fact, we've already checked out fields with 4 and 8 elements. So in this case, the key idea, when we're working over some z mod p with p a prime, it's not too tough to check for irreducible polynomials when you're working with quadratics or cubics. So when we get to quadratics, where we have to actually start doing some real work. So for example, if I take z mod 3 adjoin x, I consider the polynomial f of x equal to x cubed plus 2. Now, because we have a cubic, if it's going to factor, we're always going to be able to split off a linear factor. So to check for irreducibility, it's just enough to check on 0, 1, 2, and see if a 0 comes out. So f of 0 is 2, f of 1 is 0, okay, that we're going to look at closer, and then f of 2 is equal to a 1. So far we've found the root equal to 1. Now, note this confirms our rule from before. Okay, we found a single root. 1 is less than or equal to the degree of f, okay, which is equal to 3 here. Now, if I want to figure out how to divide, okay, we're allowed to use all our rules from before. I can use synthetic division. So when I use synthetic division, what I'll get is the x cubed plus 2 is equal to x minus 1 times x squared plus x plus 1. If we check our 0, 1, and 2 in here, we see again that 1 is going to give us a 0. So I can split off another x minus 1. And then what will be left over is another x minus 1. And we have our factorization of x cubed plus 2. Okay, note this is x minus 1 cubed. So if you apply the binomial theorem, working with z mod 3, that'll just check what we have here. On the other hand, if I consider the polynomial f of x equal to x cubed plus 2x squared plus 1, it's a polynomial over z mod 3. If we evaluate at 0, 1, and 2, we get something not 0. So that means this polynomial is irreducible over z mod 3. Now, if we form the ideal generated by this polynomial, you'll get a maximal ideal. If we take the quotient, we get a finite field. The way we should think of this field, we have z mod 3 adjoin an element u, where u cubed plus 2u squared plus 1 is equal to 0. So recall, when we take a quotient like this, I just think of this as setting all elements in the ideal equal to 0. Now that's the same as saying that u cubed is equal to u squared plus 2. We need only consider elements of the form a plus bu plus cu squared with a, b, and c in z mod 3. Okay, if we have any expressions with higher powers of u, we could use this equation to reduce them to something in this set. Well, that means we have 3 times 3 times 3 equal to 27 elements in this field. We'll say more about this when we get to field and Galois theory. To finish up with finite fields, okay, let's remember, if I have fq, a finite field with q elements, then we must have that q is equal to p to the n, where p is some prime. So the way this goes, if I take the subfield generated by 1, that'll be isomorphic to some z mod p with p a prime. And then if we check, f sub q is going to be a vector space over z mod p. It's going to have some dimension n, because we have finite field, means finite dimensional vector space. The n is going to be the exponent in q equal to p to the n. Another way to see this, f of q is going to be a finite abelian group under addition. I'll have that if I take any element, add it to itself p times, we get 0. So every element has order p, or 1 if you're the identity. So that means using the fundamental theorem of finite abelian groups, under addition, f sub q is isomorphic to a product of z mod p's. And then if I want the exponent, I just count that number. We pin down the number of elements a finite field can have. By the following theorem, that's all we need. So if p is a prime, n greater than or equal to 1, then up to isomorphism, there exists a unique field with p to the n elements. For this, we need more technique, so we save it for field theory. We'll verify the following consequences. First, we've already seen if I have two finite fields with the same number of elements, then they're isomorphic as abelian groups under addition. We have a similar statement for multiplication. So if we throw away 0, okay, we're looking at groups of units. These will be isomorphic as abelian groups under multiplication. The theorem is, if f sub q is a finite field, then the group of units, f sub q star, so we take f sub q, throw away 0. This will be a cyclic group under multiplication. So stronger than just being abelian, it'll be cyclic. Now, that means I'm looking for an element such that if we keep raising it to powers, it's going to sweep out all elements in the group. So what's happening here? If I have q equal to p to the n, the number of elements in the group of units is p to the n minus 1, and we have the group of units as abelian. We're looking for an element with order p to the n minus 1. Now, by the fundamental theorem of finite abelian groups, there exists a small stem less than or equal to the order of the group, such that the order of the element g divides m for all g in the group. Now, to see this, by the fundamental theorem of finite abelian groups, okay, every finite abelian group is going to be isomorphic to a group of the form. Okay, we have a product of cyclic groups, each with order n1 through nk. And we can arrange that n sub I divides n sub I plus 1. In this case, m is going to be equal to n sub k, so the largest of the n's. Now with that, let's consider f of x equal to x to the m minus 1. From our theorem from before, the degree of f is equal to m, so that means f has at most m roots, but we have every element of the group of units is a root of this polynomial. So that forces m to be greater than or equal to p to the n minus 1. With our assumption here, they must be equal. So that means we have some element with order p to the n minus 1, and that forces our group to be cyclic. So that's our proof. Now for examples, okay, we've worked out this result for finite fields of orders 4 and 8, and we've also seen when working with Gaussian primes, in the case of z mod p's, p equal to 5, 7, and 11. So that leaves it to you to check, okay, finite fields with order 9 and 13 for reasonable cases.